Thank you for inviting me. It's just it's a great to have this opportunity to talk about my big data visualization research here, and also learn about your work and your big data visualization needs. So let me start from here, right? Everybody talking about big data, everybody talking about the 4 V's of big data. So we have projects to address each issues here, actually. But today I only have like 25 minutes. So I plan to focus on the first 2 issues. So you will see that. Okay. So what's visualization first? Yeah, please.
Are you going to share the slides?
Yeah, I'm happy to. Yeah, I will send it to Maria after my talk. Yeah. So visualization transform raw data into pictures, right? If carefully done, properly done, right, it can often carry to convey the most essential information in the data, the information you are likely interested in. Okay? So visualization is a tool, right? It's a mechanism for you to explore your data, to discover. But in practice, visualization has been mostly used to validate your data, to validate your understanding. Because a lot of the time, people already know a little bit about data, particularly scientists, right, who put together some sort of physically based model, right, to study some particular phenomena of interest. They certainly, right, based on their training, they know something about the phenomena, but not everything. That's why they want to study it. And so a successful visualization can help them first to validate the data generated, right, by their model, for example. And even more, visualization has been used as a very powerful communication tool, right, for scientists to communicate with others their findings, right, to present their work to others. But in my opinion, right, and also based on my past 20 years of experience working on visualization problems, I see visualization is most powerful as a means to provide a good overview for your data. Particularly, we're talking about big data. So visualization can provide really, really good overview and possibly provide you, point you to a path into your data, right, for further navigation, right, for detailed analysis. And I often tell my student in my class, visualization is not a still picture. Visualization should be interactive, enable navigation, right, interrogation. And visualization is actually the interface, right, for you to interact with, for you to ask questions. So for the rest of my talk, I'm going to give you some examples, and I'm going to, because of limited time I have, I'm only going to touch roughly 3 topics. And I have to start from here because a large part of my effort has to do with scientific visualization. I know this is probably not of your interest, but then I'm just going to briefly go over it. So throughout my career, I have worked very closely with scientists in many different areas. And most of these scientists, they use supercomputer in their work. And many of them have access to the most powerful supercomputer in the world, like this one, Titan, operated at Oak Ridge National Laboratory. It's no longer #1. Okay, a couple of months ago, China's Tianhe-2 took over, become the #1 supercomputer. But it doesn't matter, right? It's a competition. And so after another 6 months, U.S. will take the lead again, right? And one time, Japan, right, had the #1 supercomputer in the world. It's called K computer. Okay, so the scientists I work with, they use such computer to conduct their study, right? And then, for example, the area from learning and studying about the universe, like cosmology, astrophysics, like supernova here, and to energy research, right? There's a great interest in energy research. Like here, turbulent combustion simulation to fusion research, right? So with such powerful supercomputer, today scientists can conduct extremely high resolution, high fidelity simulation, and which allow them to see a lot of detail, a lot of the complex interaction, right, in the physical phenomena they intend to study. But such high resolution simulation also capable of outputting a lot of data. And if they intend to store most of the data to study, they will end up using most of their supercomputing time for I/O. Right? So that's not good, because they want to use their supercomputing time for the simulation as much as possible. So we have been developing solution for this problem. And since a couple years ago, we have tried to promote this in situ visualization approach. Basically, we say they cannot, right? They no longer can just perform post-processing visualization data analysis. They have to do something during the simulation. During the simulation, they have access to all the data, right? The highest resolution data. So we can do in situ visualization, so they can, if they cannot afford to store all the data, they can at least, right, see, right, through picture, right, like animation of the high resolution, high fidelity phenomena they try to study. And because they use supercomputers, so all the visualization solution we provide must be highly scalable, must be parallelized and highly scalable. So we've been developing parallel visualization algorithm. And we also see if we can reduce the data more intelligently, more effectively in situ, right, while the simulation is running. And even better, because scientists still want to do post-processing analysis, and so we try to prepare the data, basically try to pack the data, add indexing, right, try to organize the data better to support post-processing visualization and analysis. So that's a really important technical approach. So here I'm just going to show two applications. One is in astrophysics. This is data from Supernova Simulation. So our visualization solution enables scientists to see complex interaction between different quantity, like in this case is angular momentum and the flow direction, that's the velocity field, the interaction between them. And we allow them to see their data in this fashion, this interactivity, this quality. And the other example is fusion research. So scientists actually built fusion device called tokamak, like as you see here. But then they also create numerical simulation, right, to study the design of such device. So we allow them to see their simulation data, right, realistically, and see in 3D. And they also conduct particle simulation. If they just visualize all the particles, which can have millions to billions of particles, if they just visualize all the particles directly, this is a picture they will get, which is not very helpful. Even we try to color the particle based on their property and use transparency or anything. It's so dense, so cluttered. And so we develop a mechanism for them to filter the particle based on their domain knowledge. And then they can isolate the particle, to basically identify those problematical particle of interest, and then study their behavior. Okay, that's all I want to say about scientific visualization. Now, let's switch to different type of data. And most likely, you guys are working on this kind of data, right? So most of you are either collecting big data or need to deal with big data, right? And a lot of time, what you try to find out is a certain relation, right? Try to understand or try to detect certain relation among entities, right, in your data. So in computer science, when we try to study relation, we often use a graph, right? And so big data lead to big network, big graph. Right? So to study a network, a graph, usually the first step, like intuitive way, is to lay out, right? To lay out the graph, the network. Okay. So graph drawing is a well-established field. So there have been many different graph layout algorithms developed over the years, right? And so for a small graph, like this one here, I show example here, with only 200 nodes, like over 2,500 edges, right? You can easily find a working method, graph layout algorithm, to lay it out. And then, for example, here we lay out the same graph using 6 different methods, right? And this left most 2, FM3 and the grip, they are the newer method. They were working, very well and very fast. But then, of course, for such small network, small graph, we can lay out it instantly. And okay, so it's the same graph, and we lay out with different method, and you get different picture. But they pretty much give you the same similar information, right? And then you can actually relate them. You can say, oh, this cluster, right, must be this one. Okay? So they all work and help in some way. But then one method, like this tree map method developed by us, actually try to use the space better, and then to allow you to see the interaction within a cluster better, right? As you can see, because we try to, like, unlike this one, right? There's a lot of empty space. And then for a method like this, right, sunburst layout, we use space to show the interaction between cluster better, right? So it really depends on what you're looking for. But the main point here is that there are different methods, right, for laying out small graph. But when you have a big graph, what's going to happen, right? Very complex and large graph. If you use most of the existing method, it will take forever to lay it out. Okay? But a lot of time, most of you already have certain domain knowledge. You have some knowledge about the data set you have, right? Hopefully that's always the case. So with that knowledge, you should be able to filter, right? Filter the graph to make it smaller, right? You don't have to see everything because based on your knowledge. And so you can filter the network, the graph. And here is an example, right? So we have a terrorist network And so if you just lay out it directly using the very well-known force directly method, this is what you get, right? It's because most of them know they are tightly related, and then so you get this like so-called hairball problem, right? So it's not very helpful. It only tells you that they are many of the nodes they are related, nothing else. So we can use the ontology of the network, right, to filter, right, based on what you want to study, right? In this case, we try to simplify the network, and so that we can compare two different terrorist groups, right, Hamas and Al-Qaeda, their attack behavior. So the picture then show actually quite different, right? So here, based on this picture, we see Hamas tend to launch a large number of smaller scale attacks, and then based on the label, we see they mostly attack private citizens, but then the Al-Qaeda, they launch a smaller number of a larger scale attack, and then they tend to attack government facilities. It's just the picture help you, right, compare in this case. There's many different ways to filter a graph, right? I'm not going to go over all of them, but we also develop other methods to simplify a graph to help characterize the networks. And so this is the technique we call centrality sensitivity. So centrality means importance of something. And so based on the centrality sensitivity, which means we consider how the change of importance of someone may impact the importance of others. Okay? So based on that, we can remove some of the edges, and then we can have maybe a better picture to understand the most important relations in the graph networks. So like here is an example, right? Using centrality sensitivity, we see this friend network that we can see all the cluster center negatively impact others. So the red edges means negative impact. And which also suggests that any one of these cluster center can become the most important nodes in this group, right? Because if we increase the importance of this cluster center, it negatively impacts this other cluster center, right? Usually cluster center means like important one, and means like its importance increase and others decrease, right? Okay, and we can use the same technique also to study like such co-author network, and we can easily separate the most of the node into two groups: the more collaborative group and the more competitive group. Okay. So, as I say, there's a way to simplify a graph, but you say, I have to see the whole graph. I just don't feel comfortable if you remove something from the picture. Let me see the whole graph first. So we have developed a way to give a good overview of a graph. And so as I mentioned, right, typically a graph, if you just lay out using this, like this very previously popular force directly layout, you could get this hairball problem, right? Like in this case, we have a data set we call California because it basically is, it's a web search. We get a bunch of web page using the keywords California. And then, so the network basically is the web page and the link between all these web pages. And so this data set has over 6,000 web pages and over 15,000 edges, right? Links. So if we use this well-known high-dimensional embedding method, we get this. We get the picture quickly. This is much larger than the previous one, right? Only just over 200 nodes. Here we have over 6,000 nodes. Actually, still not large, but then compared to the previous one, quite large. But this method can handle it, easily. But then the picture is not very helpful, right? You get, again, this clutter, this hairball, and then you're not using all this space you have. So we developed this fast layout method. It's not just fast, okay? I will show you some example. So what we did is first do a hierarchical clustering of the graph, and which can be done quickly. I will show you the performance number. And then we just lay out the graph by traversing, right, the hierarchy, right? And then so that we have a derived order of the nodes. And then we place the node on, in this case, a space filling curve, right? And there are different space filling curves, right, for Hilbert curve. And then with different order, you can see we effectively, right, place nodes on screen. But we still can see clusters, right? That's very important. And so let's move on. Let's just see the same California graph, right? If you remember, we use high-dimensional embedding, right? It's very fast. It takes sub-second, 0.1, 0.2 seconds. Okay, not very useful picture. And we use linlog, is a well-known force directly layout. It takes more than 10,000 seconds, right? Take forever. And then also give you a not very helpful picture. And with our method, right, we get using either a space filling curve or tree map, we get definitely some structure that we can study, right? And then here we only draw the edges, so we didn't draw nodes. But then it doesn't matter. And the clustering only take, in this case, 0.5 seconds, right? One time. You only need to do clustering once. And then layout and rendering take no time. It's like sub-second, right? So fast. And we do all this on a single computer. It's a pretty old computer. We generated this number like a long time ago. So this is, only CPU, right? Processing. We could use GPU. We could use parallel, right? We can use cluster, PC cluster, to speed up everything when you have a huge graph, right? So this just shows that on a single PC, you can handle this like easily. Okay, let's just see another example, right? This is an internet connectivity graph. So it has more nodes. It has more than 41,000 nodes, and it has over 200,000 edges. Okay, and this time we use the two like really new techniques, grip and FM3, and they take a few seconds, like 7 seconds, and this one 40 seconds. And this picture, again, useless, but this picture a little bit helpful. If we color it, we can see there are different groups. But then, when we use our method, the one-time clustering took longer, took over 18 seconds. But as I say, you can parallelize this process or GPU accelerate it. You make it like fast. And then, but the layout, again, layout still take, once you have the clustering result, the layout just take like sub-second. And this is so important. Why? Because you don't just look at the picture and walk away. You look at the picture and say, hey, what's this? You want to ask questions. You want to interact with the picture, right? Remember? So once you interact, you select a subgraph. We want to relay out. And that must be fast. As you move around, right? We want to respond. We want to respond to your intent, right? According to your intent. So that's why fast layout and rendering so essential. Okay? Okay, so far I have only talked about a single graph, right? But in real world applications, right? You guys deal with time varying graph, dynamic graph, right? In the network, the nodes edges change over time. Some nodes disappear, new nodes arrive, right? New relation established, right? So it's a tough problem. And here's just like example, we work on dynamic graph already, and we have some results. And for example, this is internet connectivity growth over 10 years period, right? We use animation and try to make it as stable as possible so you can follow the growth. But then it's really not an ideal presentation because, yeah, there are like different way. Like this is a more incremental approach. At the beginning, the layout is pretty good, but then as we move on, the quality degrades. So there are different ways to fix this problem. But then essentially, right, all the networks in the real world application are time variant, and there are different ways, right, to approach a dynamic network. Like I just show you, okay, I can animate. I just render each network, and then I play animation. You see something, right? But then people also just they select certain time step, right? And put them side by side, we call small multiples, and then you just compare them. It doesn't work every time. Or you can compute the difference. If you care more about how the network changed, maybe you compute the difference between two time steps, right? And look at and analyze the difference instead, rather than looking at the whole network. What I'm going to talk about next is what we developed called storyline visualization as a way to look at dynamic interaction, right, over time. So it's one way to look at a dynamic network. I picked this one to talk about rather than the first one or the second one. I think it's more fun. It's kind of, after work, right? You guys are all tired, so we're gonna look something more fun. So storyline visualization solution, this design was inspired by the comics we saw at XKCD, right? These people go there, right, all the time. And so there you can find pictures, right, like this picture of the movie Lord of the Rings, right, and Star Wars. And basically, artists, right, they have the skill to portray, to illustrate, right? It's interesting. The actual interaction in the movie happen in the movie. So they make it like easy to follow, right? And with this, it's artistic, aesthetic. It just looks great. So we asked ourselves, hey, can we create this with our algorithm, right? So my student gave a try, and then he come up with something pretty cool. I'll show you. Yeah, we succeed. So what's storyline visualization? Let me just quickly summarize here. Basically, the visualization consists of a bunch of lines, and each line represents an entity, and then so the line converge, diverge, depends on the interaction, right? When two entities they interact, they come close together. So when the entity disappears for whatever reason, right, the line stop. Okay, so as simple as that, right? Sounds very simple, but actually to generate that, and then the picture, you want the picture to look like what the artist create, it's not an easy job. So the first project we did, right, back to 2007, 2008, and published a paper in 2008 at a conference, the Software Visualization Conference, because my student tried to generate storyline visualization, kind of successful, but at that time we focused on the visualization of large-scale software development project. Like we try to visualize the evolution of software development using storyline. And then in 2011 and then 2012, the other student of mine look at the first student results, say, hey, we can do better. He's not close to what artists produce. So he used genetic algorithm, right, and successfully generate really cool picture, but then extremely slow. Okay. Then a group at the MSRA, Microsoft Research in China, right? They took our algorithm, they took our code actually, because one of the author, in fact, was my former postdoc. So he continued the research. He said, okay, it's too slow. We want to speed it up. So they used this convex quadratic optimization method, and then they're able to speed up and to make it more usable, okay? And then still maintain like good picture. But that's still not good enough. So my student Tanahashi, Yuzuru Tanahashi, the one who worked on who used genetic algorithm, he said, hey, I can do even better, and I can make it even more practical, because now I'm going to make it not only fast, I'm going to make it capable of dealing with streaming data, right? Real-time data. Because this MSRA's work can only deal with an existing data set. That is, they must have the whole time variant data set to generate a good picture. But now we say, okay, we want to be able to incrementally generate good storyline visualization. Am I okay? Because I already used like 30, Maria? Maria? Is it okay? I'm ready to use 30 minutes. The third speaker is here.
No, not yet.
Okay, then.
You have a few minutes. He's almost here.
Okay, okay.
Hopefully he will make it, and with questions too.
Okay, so I always prepare too much material. Anyway, okay, let's see. You guys remember Star Wars, right? And so the top picture, I don't know if you can see very well because the line very thin. And the top one was made by artists, and the bottom one was generated by our algorithm. Okay, pretty close, right? Okay, let's see another one, and then I have some zoom in so you can see better. There's another movie. We use movie because everybody's familiar with movie, right? Matrix. So this is the whole movie, right? And then we zoom in, and so I'm not sure if you can see. You can see that the main character Neo, right? This purple line, Neo kind of move between the two worlds, right? If you remember this movie, right? Move between these two worlds. You can also see the traitor, right? Cypher, kind of went to the other world and met with the three bad guys, right? They always, right, appeared together, right? You remember the movie? So, from this you can see, right? You can see the development of the story. Sorry?
You get the feeling that the guy who wrote this algorithm studied the artist's version first.
Yeah. Actually, that student actually studied the whole script. And that's even a more complex, interesting movie, Inception. I watched the movie the first time. I didn't really understand, but my students' storyline helped me. So this is the whole movie, and this is just zoom in, and this is like, you remember the dream within dream, nasty dream, and then you can see here that each dream you must, before you enter, everybody enter the next dream. They're better somebody stay in the current dream so it can wake up everybody, right? Something like that. So you can see that happen. But then it didn't happen later, so that's why the movie became more interesting. But anyway, okay, I hope you get the idea. And here, because I mentioned about dynamic network and we can deal with streaming data, right? Here's an example showing you, okay, I need to. This is Star Wars, right? It's a simple one, small, but then just proof of concept, right? As more data come in, we need to refine the layout. So periodically we refine. But then we try to make use of the space we have.
And what's the data set limit for this kind of streaming visualization?
What do you mean?
Because as I'm looking at this, it keeps getting smaller, smaller, and smaller, and there will be a point where I'll really have to get a really powerful magnifying glass to see what it is.
Okay, sure. As I say, this is not a static picture. You should be able to stop it and say, I want to zoom in, right?
Okay.
Yeah. And then, because this just shows interaction between two entities, but then there may be more information each carry that you want to investigate further. Okay, let's look at the larger one. This is a Enron Scanto, everybody know about. And then there's an email data set we can look at, and it has almost 500,000 email messages, right, among 1,264 employees. And this is over a 3 years period. And we're not certainly, well, I mean, this video student just made for me, we're not looking at everything but the first 500 time step. And then you see it's become exactly the problem you just point out. It becomes denser and smaller, right? You cannot really comprehend. But then I just want to give you a sense what it will look like when you look at a large data set. But then as I say, right, you can, you can move around, right? You can zoom in. Or you can filter. I mean, you can always filter the data, of course. Okay, I think that's all I want to say. And there are more I can say, but then maybe you can invite me back. I'll talk about something else. But why? Because we have a lot of different projects. But then I just don't have time to talk all of them. Just give you a sense what we work on at this moment. And for example, right, do I still have another minute? The healthcare data, right, the health record, patient record data, we currently work on. It was not easy to get the data set, but then finally we have it. And here just showing that we can actually study, in this case, it's a kidney disease patient, and we look at the development of the, each patient there. There's like a couple of hundred patients here. And then, so here are those patients who are actually dead, And then we can trace back to see the different color represent different symptoms. Like, and then there's, I don't know if you can see, there's like a gray area behind. We don't display everything. Depends on what the user want to study. We hide certain information, but here just show like what kind of symptom each patient has, or like how many patients had this kind of symptom or that kind of symptom, and so then this may help physician, clinical researcher, even policymaker, right, to understand, right, some of this medical problem. Anyway, I think I should stop so that you have a chance to ask some questions. Yeah, this is my contact information, and thank you very much. Okay, let's there first.
So this new visualization technique that you're showing us, is that patentable, or is that a new way of looking at things? And do you have software that you are going to commercialize that everybody can use?
I could, yeah. Do you want to invest? I think some people actually already successfully, right, put together visualization software, and then they make a lot of money. And I have not tried that. I mostly just identify new problem and then new topics, and then work with students, come up with a new approach. We prove it works, and then we move on to the next problem. And so here I should emphasize that, for big data, right, visualization is definitely a very important tool, but it's not going to replace some of the existing method, right? You're not going to replace data mining, machine learning method, right? So, but it's a good, it's supplement, right? It's a good, supplemental tool, and so it can it's complementary, basically, what I'm saying. So, for example, I try to show you its visualization. If you have the appropriate tool, you know how to make visualization properly. You can have a good overview of the data. Sometimes it's so helpful, right? It guides you like where you should focus on, right? That first picture. But certainly there's like, okay, maybe you want to approach the problem differently. You don't start with an overview, right? You can start with like a subset of data, and then maybe grow your understanding from there, right? Also visually, that's possible. So our job is to develop like all these different ways for you to look at your data. As I say, there's four V, right? There's a different type of data also, right? And then also the incomplete data. There's a lot of problems we have to deal with, like how you incorporate uncertainty, right? Uncertainty due to the data generation process. Even uncertainty due to the data transformation and the visual transformation that you just did, right? How you convey that to the viewer, yes.
I have a question about the storyline visualization,
Sure.
especially in the streaming case. The number of clusters, is it predefined, or is part of the visualization, or is some other data mining that you have to do data crunching to come up with?
This is a very good question, right? The clustering, just like the previous layout method, also rely on a good clustering strategy. And at high level, basically, if two entities, they interact in some fashion, right? Their corresponding line or two come together, right? But then you have to define, maybe there's a threshold, something like how you consider they actually interact. What do you mean by interact, right? So I think that's like what determines like how a cluster is formed, how the group is formed. So this is less. It's less about like the traditional data mining or machine learning method.
So in the streaming case, is it dynamic also?
Yeah, it's based on a greedy algorithm, the last one. Yeah, it's dynamically, right? And then we keep refining the result, because after we have more data coming in, right, the layout becomes suboptimal, and then we try to improve it. Yeah, but clustering definitely the key. Yeah. Yes, please.
Yeah, I was wondering if you guys contribute to any particular open source libraries or packages?
Actually, my student, for example, the fast graph layout algorithm, we have libraries, and we already provided to like FBI analysts. They saw our paper and they asked for the code, so we provide the library. And we also, basically we can make it available. We probably didn't publicize it, but then it's there online. And then for the storyline code, the first version, like the slow, but then still give you a good picture, that one is online. But then now we have this better version, right? Can deal with dynamic data. And that one, after we publish it, hopefully this year, we will make it available. Yeah. Whenever people ask, we typically just make it available. Yeah.
Is it linked on your
Sorry?
Is it linked on your website?
It's hidden. Yeah.
Can we send you an email?
Yeah. Sure.
Yeah?
You can play with the old code first, and then we can keep you updated. Yeah. No, because it's also a responsibility, right? If you want to make something open source, you want to clean up the code, and you want to provide documentation, even like support later, right? But then most of our students, they finish the project, they left, right, for their job, and then we really don't have the continuity, don't have the resource to. And then, most importantly, they didn't have time to clean up the code to make it like reasonable enough, right, good enough for people to actually use it, easily adopt it. And when I'm not happy with the code, right, then I didn't want to make it available just like that publicly. It's not like we don't want to, it's just like we didn't have the resource. Yeah.
Yeah, if you go back to one of the slides with your visualization.
Which one?
You had two in a row that were like they had different networks right after the terrorist layout. Yeah, in these ones.
Yeah.
So one of the issues that I have when I work with this kind of networks is not so much the time it takes to render the layout the first time, because the first time it can take a few seconds. But then if I remove or I add a node, the layout using one of the force director layouts is very similar. So the adaptivity is really fast if you just add a node or remove a node. What's really interesting, at least to me, in that case, is how the clustering may be impacted. So I might need a faster way to do clustering rather than like really visualizing.
Basically to modify the cluster.
Sort of update the clustering to see if the structure
Yeah,
changed.
we have to, because we need to, we actually apply this, we extend this out to deal with dynamic network, right?
Yeah.
The animation exactly show that. So we have two different ways, right? One is assume we have all the time step, we have all the data. Then we can do a global, right, optimization. Right, and then to come out with like a good layout for the whole sequence. Or we do it incrementally like the one I show you, right? We lay out each one, basically we cluster, right, each time step independent of other time step. And then we try to find the correspondence between cluster. Because we have to identify, say, this cluster is, in this time step, is this cluster, right, in the next time step. And then, so then, basically, through this process, right, we need to know, like, we need to deal with, like, node disappearing or new nodes, right, come to a picture. And so, yeah, we have to deal with that. It's still ongoing project, effort now, like how we really deal with, come up with a good clustering method for dynamic network. It's not our strength, but then we have to deal with that problem. Yeah. Do we have the third speaker? Okay. Okay, I can answer more questions or give another talk. No, just kidding. Yes.
I had one kind of half-baked question. You seem to be looking at the data exactly as it's supposed to be, with nodes and edges. But do you ever do any funny things with the data, like take Fourier transforms or anything, and just look for funny patterns?
You mean if we try to study more the rates or something?
Yes, stuff like that. Yeah.
We have not, but then we certainly could. Again, right? It really depends on what's the purpose, right? When we work with, when data come from somebody, right, and we usually will talk to. A lot of time we use like public domain data, but then the best is we work with somebody who actually generated data, and then they can tell us what they're looking for, what they care about. Like you say, what do you care about? Then we will focus on that more, right? So really, we need to know what do you try to find out, right, from the data. Then we will, right, develop appropriate solution for it. Yeah.
Sometimes you can see things that you didn't even suspect were there.
Yeah. Sure. Yeah.
I think, well, if it's up to you. We can take a 5-minute break.
Yeah, I think.
And you can take the opportunity to have one-on-one questions with Kwan. In the meantime, the other speaker literally just arrived and is
Yeah.
in the elevator. So he should be here.
Yeah. I would suggest we take a break because it's been more than an hour. I think people are tired. They need beer or something.
Take a break. We had a 15-minute break scheduled, probably shorter break, and 5 minutes, 10 minutes. We will be here, and we will go on with the next speaker. We will have to have a shorter talk for him, but it is good that he just made it in the nick of time. So thank you.
Okay, thank you.
Thank you so much. Thank you for this.
I'm curious, what